I'm pleased about this topic, and Michael Mahoney is from Stanford University in the math department, and has been working on the area of network analysis and clustering and topics that we share an interest in about how to get insight. I love the title, extracting the insights from large networks. Michael, I'll give you the time here.
All right, thanks. So this actually has to do with exactly what we're talking about. You want to get insight into large networks, and it's not clear that that matters, right? There's a lot of applications where insight doesn't matter so much. I have a question. And what's an example of an application where insight doesn't matter much? So there's a lot of think of it. There's a lot of internet applications, for example, where the goal basically is to optimize the next user interaction. And if you do a little bit better job at optimizing the next user interaction, that means a big revenue return next quarter. And so, it's maybe arguably would be better to come up with a slightly more complicated machine learning model, but only slightly. Spend your time generating gobs more data and cleaning that up and fitting the model. And so if you don't really understand what each feature is doing, that's okay, because that's not the goal. There's a lot of applications though where there's not a very well-defined objective like that. And what you'd like to do is to use this sort of network analysis to get some insight. And so that's what I'll be talking about today. And hopefully that's obvious, but if it's not obvious, I'll give you some examples of why that's going to be the case. And one of the tricky things is that I think most people have some sort of intuition about the way data look and the way clusters look. And if you're familiar with high-dimensional spaces, one of the things is that high-dimensional spaces are very different than low-dimensional spaces. And when you don't know that, it's at first very strange and counterintuitive, but once you've played with that a little bit, you realize high-dimensional spaces are very different. And you start to get some understanding of the way those high-dimensional spaces look. And then it turns out, what if the data is neither sort of high-dimensional nor low-dimensional? Maybe it's the worst of both of those. And so, how can we quantify these ideas, and if the data in fact look that way, how would you get some insight or understanding of what's going on? And so, at the end of the day, what we're going to see is that in a lot of these cases, some sort of what I'll call small-scale structure. I'll quantify what I mean by that in various ways, and something about large-scale structure. And when you have intuitions in the back of your mind, whether data is very low-dimensional or very high-dimensional, you're making certain assumptions about the small-scale structure and large-scale structure, and that those assumptions may or may not be, in fact, the case in the real data. So I want to start sort of with the bottom line. This is a conclusion slide. So I'll show you this slide again. And in a sense, everything between this slide and the time I show it again is bells and whistles. Okay, so this is the main point, and this is the really sort of important point. So think large networks, and I'll give you examples of ones we think about, but I think the following holds for a very, very broad class of what goes by the name of complex networks, social information graphs, or whatever. And there's a common picture that people have in the back of their mind. So occasionally it's made explicit, but typically it's some sort of implicitly accepted picture. People just assume that it's the case. And that is the following. As graphs corresponding to complex networks become bigger and bigger, the complexity of their internal organization increases. You want to find the needle in the haystack, and it's just sort of an assumption that the needles are there. That that as these graphs get larger and larger, they have some internal organization. There might be some hierarchical structure. There might be any of a range of other structures. But as graphs get larger and larger, the sort of complexity of their internal organization increases. So what I want to say is that empirically, and basically I'll spend the hour describing to you the empirical results, but empirically I think it's fair to say this picture is just plain false. Now, what we're doing here is trying to prove a negative result, and that's always tricky, right? So I need to convince you that it's not because we were stupid or lazy that we couldn't find this internal structure. That in very strong senses of the word, this picture is false. So we have very strong evidence. But moreover, I want to say the falsity of this implicitly accepted picture really, really should be obvious. If you really believe common small world with preferential attachment models, right? So take a step back and ask, what are these small world and preferential attachment models assuming? Small world models say you start with some underlying structure, usually it's some underlying geometry, and you add random edges. And you add random edges so that you get some sort of local clustering, and you're random otherwise. Namely, you have some sort of local clustering, you have some sort of local structure, and you're unstructured otherwise. Namely, that's not going on. Preferential attachment models say you have a bunch of nodes, and you can characterize different nodes in various ways. The simplest way might be the number of connections they have, so the degree. You can characterize it that way, and otherwise you're pretty random. All right? So if you really believe small world and preferential attachment models, you won't believe that. Now, that being said, the implications of this are significant enough and counterintuitive enough that when you go down and you sit down and you make design decisions as to what data analysis tools to use, what machine learning tools to use, what questions to ask of the data, you're probably going to implicitly assume the opposite of this. Namely, you're going to assume this. All right? And so I'll walk you through that. So the most obvious example might be you want to do recursive, my favorite and variants of, you want to do, say, recursive spectral partitioning or some other sort of recursive partitioning. What you want to do is to split the data into two pieces and then recurse. Split this into two, split this into two, and so on. And the idea you have in the back of your mind is that you're splitting these into two pieces that are about 50-50. So you have a 1,000,000 node graph, 500,000, 500,000, 250,000, and on down. If you split this into two pieces, and it's 100 nodes and 999,900 nodes, and so on, you're going to think that's sort of unsatisfying. Algorithmically, because your recursion depth is going to be pretty deep. Statistically, because this could be some artifact of noise. So for a range of reasons, you're going to find that unsatisfying. But that's in fact going to be the case. So you're probably going to either pre-process the data or do something to basically not have that happen. So this is going to have very, very significant implications. So I think this is important for the understanding of social and information graphs in the first place, but more generally, it has very, very significant implications for data analysis on graphs and more generally. And the reason is common machine learning and data analysis tools make very strong local global assumptions. For example, the recursive spectral partitioning. And really, they're exactly the opposite of, call it local structure on top of global noise. Little local pockets of structure and global noise. Because if you can split it to 50-50, what you're saying is at the very largest scale there's an organization, and you can split and recurse. So the tools are making exactly the opposite. You're saying there's a global structure and a bit of noise on top of that. And what the data will show is that there's going to be some local structure, but really you're empirically pretty quasi-random at the largest size scale. So is there a question?
What is the definition of a complexity here?
So this is the high-level picture. I think these conclusions are going to hold more generally than any particular instantiation. Most of what I'm going to talk about is going to answer exactly that question. So I'm going to have a precise definition of a couple things. This work grew out of some work trying to understand clustering in communities. So there's a large body of work on community detection. And so I'm going to be talking about it in that context. And it becomes something called conductance. I'll describe what that is and say whether it's more appropriate for some of the other measures. There are graphs for which we know that that particular measure isn't the right one. And then I'll mention that a few times and point out how the results might change based on that. So I'm going to get to that.
Thank you.
All right? So, implications for understanding networks and data more generally. So, basically, diffusions or some sort of diffusive processes appear under the hood in all sorts of guises. So if you're interested in viral marketing, you want to go out, you want to find the 10 most influential people, give them free tennis shoes so they'll walk around the streets and everyone will go, wow, the cool people are wearing my tennis shoes, I'm going to go buy that brand of tennis shoes. You want to control epidemics. So in this case, you want to spread the virus, you want to control epidemics because you want to prevent it. Who are the people you inoculate? Maybe they're the ones that are not most obviously worthy, but they're the ones that are going to minimize the diffusion of the virus. Query refinement. You're at an internet search engine, and the way you might not bid on just this phrase, you might bid on this phrase and phrases like it. What does it mean, phrases like it? How do you define it? You look at the corpus, you define the similarity notion, and you diffuse a little bit. And so on and so on. So at the high level, you should think, low dimensional structure, there's probably some sort of clustering going on. And really, relative to combinatorial objects like graphs and strings, we could ask combinatorial questions. You have some sort of implicit capacity control. and it provides a bottleneck to diffusions and mixing. High dimensional space intuitively doesn't, because in some sense everyone's pretty close to everyone else. And diffusive processes, so now you imagine diffusion, and oftentimes technically this is characterized in terms of the second eigenvalue of a certain matrix. Diffusions are going to behave very, very differently if the actual set of nodes that is the worst case bottleneck is 50-50 versus 99.9 versus 0.1. Right? Because if it takes a certain amount of time to get out of a bottleneck, if that bottleneck is 50-50 of your graph, it's going to have a hard time getting to the other side of the graph. Whereas if the bottleneck is very, very small, you just wait a little bit of time and you're going to get out of that bottleneck. So diffusion is going to behave very, very differently. And even if you don't care about viral marketing, controlling epidemics, and so on and so forth, you probably compute eigenvectors. I mean, eigenvectors are a diffusive process. You look at the way eigenvectors are computed, they're basically a diffusion. In the simplest case, a leading eigenvector of a class of matrices, you can basically exactly compute with a diffusion. And more generally, do some sort of iterative method. So, that's an example of a machine learning or data analysis tool that boils down to something like this, even if you don't care about these particular forms. I gave you an example of a recursive algorithm, and people find the idea of a few large clusters and a huge, huge number of small ones is sort of unpalatable, non-interpretable. So that's, if that's the way the data is, that's the way it is, but people find it unpalatable. Okay, so lots and lots of networks out there: technological communication networks, biological networks, social information graphs, financial language networks, so on and so forth. So this work grew out of it. So what I'm going to talk today mostly about is social and information graphs. And you should think, collaboration networks, friendship, post citation, blog cross posting, advertise a bit of phrase graphs, and so on. And this line of work actually started when I was at Yahoo in the research division, and I was a resident matrix expert. Two different research business units came to me and said, basically, we had this problem, and the problem boiled down to finding good clusters in the graph, and at a sort of a very high level. And the goal there was to do better advertisements, because that's where the revenue comes at places like Yahoo. And we saw a number of very strange results, and it seemed to me to be the case that if those results were true, meaning not an artifact of our algorithms, not something we were doing wrong or whatever, it could not be peculiar to those two advertise-a-bit phrase graphs. It had to be worked out. So then we went back and looked at, on the order of 70 by now, mostly publicly available graphs, and since I looked at a bunch aren't yet, and asked, are these properties true more generally or not? And so the short answer is yes. So what I'll be talking about today is the leading bit of information, the leading, the most sort of significant difference. Now, every one of these 70 graphs is going to be an exception to what I'm talking about today, right? Every one is going to have details a little bit different, and any graph that you have probably is going to be different in detail. But what we saw is that, the leading order piece of information that we saw in all these data sets was very, very different than people had in the back of their mind and so on. But everyone's going to be a little bit different. So to give you a feel for the sort of types of data we looked at, so this was in the very first paper, 10 of the 70, not particularly large or small, but to give you a representative feeling for the types of ones we looked at. So a bunch of social graphs, live journal e-themes, Flickr, Delicious, authorship graphs in physics and computer science, information graphs, you can think of citations and blog cross postings, a bunch of snapshots of the web, authored a paper bipartite graphs. These bipartite graphs are structured probably the closest thing to the advertising bit of phrase graphs, which are also bipartite. Some differences, but those are probably the closest publicly available ones. Snapshots of autonomous systems and Neutral and so on. So, a wide range of data sets. And one thing to note is, for example, say you have 4 million nodes. How many edges do you have? 40 million, 40. So, there's a degree of variability, so the mean is maybe not so significant. But just to give you a mean, you're talking about 10 edges on average. So extremely, extremely sparse. All right, we'll get back to that. But extremely sparse and pretty noisy. Okay, so here's a particular example to say how it arose. So the graphs you think about might be a little bit different, but just to give you a little bit of context. You're at Yahoo, although Yahoo's been having a wobbly time the last couple of years, so maybe I should change this slide. But at least back then, Yahoo's doing search. You enter something into the search box. Up pop a bunch of search results, and up pop a bunch of advertisements. And so the users usually care about this, the search engines care about this, because that's what raises the revenue. And so, how might a graph or network arise in an application like this? So you construct a keyword advertiser graph, a bunch of keywords on one side, a bunch of advertisers on the other, And the goal, you put a link here if the person advertising bids on that phrase or whatever. There's a range of ways you can do this. And the goal is to mine this graph to provide you advertisements to optimize click-through rate or ROI or any of a bunch of downstream metrics that the business people care about. So how might clustering arrive in these sorts of applications? So you might do marketplace depth running. You want to find new advertisers for a particular query or submarket. You might want to do query recommendation systems, suggest new advertisers new queries that have a reasonably high quantity of clicks. So the search engine might want to do this because they have logs that they know people clicked on, and they want to suggest a new advert, a new query to the advertiser that might broaden his or her market, or that may be a little bit finer queries. So they're not bidding on the most common terms; they're bidding on something a little bit finer, and so they would actually get more bang for the buck if they bid on something finer rather than a very common query. Because deeper markets are bidding on broader queries. So a range of different things like this. There's a lot of microeconomic and natural language issues that I'm going to be ignoring here. But that's sort of roughly why it is. The other reason, contextual query broadening, something similar. The other reason why you might be interested in this is you want to do something called bucket testing, or A/B testing sometimes. And so you want to split the users into two different groups. And I want to know if I make the letters bold, if I change the color from green to blue, if I do this sort of thing, do I get more clicks? And clicks being a proxy for satisfaction.
Sorry. In this clustering questions, there are two types of problems that run into them, apart from Yahoo from the others, that they don't seem to have to done. One is, can you do clustering with multiple criteria or even multiple logical rules and things like that well? And B, do clustering according to a model that has sort of causal dependency. In other words, if you think of the tree, the model of a group, and you're going to create a cluster by stepping through the tree, like we do, for instance, in all the oriented databases, where you actually try to look at your data from the eyes of a model.
So you're not talking about there's not a temporal variation, it's more conceptual or causal.
Logical. I have in other words, I know the difference between that, for instance, this and that,
Yeah.
that. And I want to take advantage of that.
Yeah.
When I do my.
So, there's a lot of work, and I'm sure there's work on that. I haven't seen anything along that that's really satisfying.
Right, because I mean, the fellow from Yahoo was here, and he was telling me that one of the problems they face, they want to do policy-based searches for traffic.
Yeah.
They don't have good tools for that.
Yeah. So I don't know, I mean, probably the thing we should talk offline afterwards, because the leading order bit of information on what I'll be talking about is there are not good large clusters. There's good small ones, there's not good large ones. So you're in trouble. Now, that being the case, it's definitely the case that if you look at medium-sized things that we pull out of medium-sized clusters, they're definitely not random. I mean, there's definitely something going on. And so, from our perspective, if we do a diffusion, we truncate in various ways, we do other tricks that can be interpreted as regularization, we can make those clusters better or worse. So I suspect, it's far from immediate, but I suspect those sorts of ideas could be coupled with this in some sense as a prior. And so if the data happen to be nice, you could use it, which is probably how people are thinking about it typically, using it as a prior to say I'm going to go here rather than there. And so I suspect you could couple those ideas with this, but it's not, probably not
For
immediate.
instance, you like people are doing similar things in learning or sensing in graphical models, and then use appropriate priors to try to capture that.
So I'm using prior in the same sense. Technically, we'd implement it differently because of size scales and stuff, but that's what I mean, yeah. All right, so the idea that people have in their mind is the following. The goal is to find isolated markets or clusters with sufficient money or clicks and sufficient coherence. So it needs to be big enough that it's worth spending your engineer's time on. Sufficient coherence that if you want to pull it out, you want it to be meaningful in some sense of the word. What's usually not asked is this even possible? So there's a pipeline in terms of the data analysis. That you have some goal, you quantify an objective, you try and find something. If you don't, you iterate on that process. Change the objective. I want to find good communities. If you can't find a one-way, change the definition of what a community is. Change the approximation algorithm or heuristic you use. If you don't pull something out, you iterate that process. And eventually you find something, and then you can give it to your manager, you can publish a paper, whatever. What's usually not asked is this even possible? I mean, can you test the hypothesis that the world looks like this? That there's a gambling cluster and a sports cluster, and maybe there's an intersection of sports gambling. That's what I want to pull out, because that's relatively high revenue terms. All right? So the tools that I'll be talking about today will basically you can think of them as tools that will allow you to ask this question, and test the hypothesis that the world looks like this. So what you're thinking is that, there's a couple clusters, there's intersections, maybe there's a hierarchy here. You can quantify this in various ways, but k-means or something like that. 3 means is going to pull that out. And most other clustering objectives, if you are careful, will pull some variant of them out, right? You might need to argue about this objective or set it going to do something very fine. But to a first approximation, that 3 means should work on something like that, right? Is this even possible? Is this what the data even roughly looks like? So people think about these things in terms of graphs typically, and there's a range of ways you can model this at more bells and whistles, but for today I'm going to be talking about a graph. A bunch of nodes, which are things, a bunch of edges, which are pairwise interactions between things. So I'm not going to talk about time dependencies and directedness and so on. Some of the results we extend, we'll extend immediately. Others, it's a lot more non-trivial. And the first thing to know is that graphs are sort of combinatorial and not obviously geometric objects. And the geometry here is nice because people like it because they can get at statistical inference questions, basically. So the strength of this is that it's a powerful framework for analyzing complexity. So if you really want to work on a million-node graph, you're coupling with databases and so on, you need to worry about complexity issues. And not in the sense of complexity theory, just in the sense of algorithms. The drawback of this is that geometry is really very useful in machine learning and a range of other areas for doing inference, but it's a very different way to think about the data. And so the question is, if you're doing this, you can talk about this in terms of k-means as a combinatorial objective, but this is a geometric thing. It's a data set that's living in 2 dimensions. And the proof of that is that there's a picture, and the picture is on a 2-dimensional whiteboard. So how do people think about these things? So people think about networks in various ways. Here's a schematic illustration that we pulled from somewhere. And, of hierarchical clusters. So there's a global scale, there's a smaller scale, and so on. And inside the smaller scale, we get smaller scales. And this seems like good evidence of hierarchical clustering. So this is one of my favorite pictures, actually, because we took this from someone when we were just beginning this work. And this is an actual data set. This is actually markets. The reason I like this picture is I think we got it originally as an EPS file from someone. And you convert from EPS to JPEG to TRAW back to EPS or something. At each time, you lose a little bit of resolution. In particular, stuff off diagonal tends to become more white, and stuff on diagonal becomes a little bit more black. And you say, geez, once you've done that 3 or 4 times, that looks like it's pretty good diagonal cluster. So this looks like a stochastic block model should work. This looks like a bit hierarchical like that. So maybe that's right, maybe that's wrong. So can you test that hypothesis? Can you test whether that's the case, or whether we're really viewing something that's an artifact of the fact that I changed file formats a few times? So here's what these graphs actually look like. Nothing like what's shown on the previous page. And this is a particular visualization. We use a publicly available visualization software, and we're visualizing a publicly available network. So you could probably tell me what visualization software we're using to visualize this, based on some artifactual things here and there. You wouldn't be able to tell me what network we're visualizing. So these visualizations oftentimes, when you get to reasonable, not even very large scale, I don't know, this is 20,000 nodes or something, so not even very large scale, even medium and large scale, oftentimes reveals more about the visualization software than the graphs they're trying to visualize, which is a little bit humbling. But on the other hand, it says, geez, if we're really revealing more about the tools than what we're trying to visualize, can we use artifactual properties of those tools to try and reveal insight into what we actually want to understand? So at a high level, that's sort of what we're going to be talking about. So what I want to say is, these graphs have some sort of nice structure. Call it a local geometric structure. A couple clusters. I can put on a plane. This is Zachary. If you're familiar with that. Zachary's a line. There's a left half and a right. This is Newman's network science. Similarly, you put it on a plane. We just stretch things out just a little bit to have a nice visualization, but you can cut that off, and then you get something meaningful. All right. And what I want to say is these graphs don't. And if they have some sort of structure, it's a lot more subtle and counterintuitive. So the fact that I gave you one visualization doesn't prove that. The fact that 10 visualization algorithms give you something equally non-interpretable suggests that. And what we'll be talking about later today will prove that. So the question is, can we sort of take the tools people use, SVD, latent semantic analysis, that have sort of strong geometric assumptions that buy you a lot in terms of inference and prediction and machine, and maybe do a local version of them, because we've seen that oftentimes there's some sort of local structure, and then have them maybe degrade gracefully at larger size scales. So the claim is going to be that most, or all, large informatics graphs have some sort of local structure that's meaningfully geometric or low dimensional or nice, and do not have analogous global structure. So I'm going to talk about a particular, I'm going to talk about a particular way to formalize this. And there's other ways. So to give you a bit of intuition in the background, I want to ask the following question. You and your 100 friends, you probably have 100 friends on Facebook. That's, sort of a median number, or so. And the usual thing is to say, the 100 friends on Facebook cluster into a couple of clusters. The college friends, the high school friends, and the work friends, and the family friends. And so those are your one-hop friends. Now, ask, what does the graph of you and your 100,000 closest friends look like? And do you think there's analogous, there's half dozen clusters that are meaningful in that graph? And the answer is, of course, there's no way on earth there is, right? So, what about you and your 100 million closest friends on Facebook? I mean, no way that's the case. So, Facebook's actually an example where the conductance measure I'll be talking about later is not the right one. Because the size scale 100, the local clusters actually do sort of couple the higher degree nodes. So it's another notion of clustering, local structure that we're working on how to formalize. So this is good for intuition. This particular example is not going to hold for what I'll be talking about later, but other notions of local structure will. But to give you some intuition, what is the graph of you and your 100 friends on Facebook look like? What is the graph of you and your 100,000 closest friends on Facebook look like? So lots of questions you can ask, degree distributions, cluster communities, how they grow and evolve. Oftentimes you want to do the dynamic process of search and diffusion. What's the best way to do machine learning if you want to interface to that? So I'm going to be talking about clusters and communities. That's think of that as a slightly more refined thing than degree distributions, clustering coefficients, namely probably the triangle scores. Because what those metrics are trying to capture is something like that. But what we'll see is that they're just very local things, and that intuition sort of doesn't propagate out to larger size scales very well. When I say very well, meaning if you try and get 100 node clusters rather than 3 node clusters, algorithmically, statistically, in a lot of ways, things become much, much worse. I'm not going to talk about time-dependent issues and so on. A lot of what we understand here, we have a pretty good understanding of what some of these things look like. There's actually not many publicly available datasets that are good with respect to that. So I'm not going to be talking about that today, but we'll be talking about it in questions. So the usual approaches. Heavy-tailed and power laws. What you say is that at large size scales, so you have extreme heterogeneity in the local environments, and this is captured by a very, very simple statistical degree distribution, and you're fairly unstructural otherwise. And this is based on preferential attachment and a whole bunch of models. Another very different approach is local clustering and structure. So that's very small size scales. The local environments of a node have some sort of structure. When you start with the geometry and just add random edges. That's in some sense meaningfully geometric. And this is the basis for small world models that start with some local geometry and add stuff and random otherwise. So we want to ask, can we take those ideas and how robust are those ideas more generally? And the way we're going to do that is to treat the graph as sort of a thing we want to try and understand that we can't really visualize. And we're going to want to use experimental tools to tear the graph apart and to test the hypothesis that the graph looks nice or not. And so what we're going to do is use graph partitioning. So graph partitioning is a family of combinatorial optimization problems. We want to split the nodes of a graph into 2 sets that satisfy by criteria, that not much edge weight crosses the cut. So the cuts are good cuts. And both sides contain a lot of nodes. So there's a bunch of ways to formalize this. Graph bisection, 50-50, beta balance bisection, 70-30, quotient cut vectors, expansion if you're familiar with that, conductance, normalized cuts. Conductance and normalized cuts are a variant of expansion that's appropriate when you have degree variability. Conductance and normalized cuts are the same thing. There's a slight technical difference that's irrelevant to what we're talking about today. So all of these formalizations are intractable. So I don't know if that's good or bad. But what that says is that we formalize our intuition in such a way that we can't possibly test. The next best thing is we can apply some sort of approximation algorithm, because that's what we do. All right, but here's the basic idea. So this work grew out of trying to find good communities. And so the way most papers on community detection starts is to say, everyone knows that networks have good communities. We don't really know what communities are, so that's not so good if you're on thin ice when you say you don't know what the communities are. But the intuition is that there's more edges internally than between you and your complement. So conductance is probably the combinatorial objective, meaning an arbitrary graph, the combinatorial objective that best captures that tension, internal connectivity versus external connectivity. All right? It's far from perfect. I'll give you an example later about illustrating why it's far from perfect, but it's far from perfect. But it is probably the objective that most captures. You know, there's other objectives. You can use something called modularity. So if you think of conductance as a sort of a surface area to volume, the amount of stuff going on inside you versus the rest of the world. The metric known as modularity captures one of those by criteria. It captures volume. Minus a statistical correction that for very small graphs is non-trivial. But when you get to large graphs, empirically you can ask, and that statistical correction is a lower order term. So if you're using modularity to define clusters in large networks, what you're saying is that if you're using modularity to define communities in large networks, what you're saying is good communities are large clusters, basically. So I don't have strong feelings about what the definition of a community is, and whether conductance is a better measure for communities than modularity. If you think big clusters are good communities, then you should work with modularity. If you think that communities are things that have this tension between internal connectivity and external connectivity, you can ask whether modularity is capturing that. The answer is no. And conductance captures that relatively well. So it's a combinatorial objective that captures that best. But even if you don't care about clusters and communities, this is interesting because one, it's going to be a discriminative statistic for things we'll be talking about. And two, it has very, very close connections with diffusive processes, with geometry. If you're on a low-dimensional space, conductance is surface area to volume of the lower order term, a most arbitrary graph. If you want expanders, which are the graphs that embed at least one of the low-dimensional spaces, we know how that behaves. So this is an objective that we understand. So why are you worrying about both criteria? Why we're worrying about both criteria is the following. So some graphs, let's call them space-like graphs, finite element meshes, things that arise in PDs and scientific computing, more or less anything that lives on the Earth, like road networks, random geometric, cut quality and cut balance work together in the sense that I'm going to show you a bunch of plots, and on all these plots, the x-axis is going to be size, y-axis is going to be quality measure. Down will be good. It's surface area to volume. So if you have more stuff going on inside, that's good. So there's a ratio down is good. So in all these plots, down will be good. And if you ask, how does cut quality and size work together? Are bigger circles better or worse than smaller circles in terms of surface area to volume? So bigger circles are better than smaller circles. So this plot goes down. All right. Are circles better than triangles for a given size? Circles are the best shapes in terms of surface area. This is just isoperimetric. It's a fancy name for this. So this plot will go down as a function of size. All right. So the intuition should be that this plot should go down because qua that objective, bigger things are better than smaller things. And so in some of these space-like graphs, these two work together. And it's an empirical question to say, how do these things behave more generally?
To describe the separation in communities with these two metrics and metrics that are associated mostly with the things, is that correct?
So this is basically an edge-based clustering metric, yeah.
But one could actually get the dual formulation where I look at how the nodes, let's say,
Yeah.
and then the people or the elements in the structure, how they discriminate from each other, and how they capture similar features. In other words, the quality of the cluster versus the isolation.
So this is, conductance is defined, I don't know if I have it on a slide or two here, or,
So how are the two related?
so maybe I don't have it here.
If you want to talk about it, it's
I guess not. So the conductance of a, maybe I'll put it here. So the conductance of, so I have a graph G is equal to V comma E. And let's say the conductance of a set of nodes, this is a subset of a vertex set, is surface area to volume. By which I mean it's roughly it's the number of edges inside your cluster versus the number of edges crossing. Not exactly that, but basically that. That's the conductance of a set of nodes. And the conductance of the graph is the min over all S of phi of S. So it's a measure for nodes, but it depends on the amount of stuff inside the cluster versus crossing. And we're going to ask about the size or golf version of that question. So I said that this is intractable, and so the intractability is a bad thing because you can't compute it. But on the other hand, graph partitioning is a nice problem because there's a wide range of methods that have been studied in theory and in practice, and a bunch of different types of practice for asking how this behaves. And so roughly what's going on in terms of the lay of the land here is you have spectral methods. Spectral methods compute eigenvectors of certain matrices. You compute an eigenvector and use that eigenvector to partition. There's flow-based methods. These depend on single commodity or multi-commodity versions of max flow, min cut ideas. Totally different method. No eigenvector, totally different method. Both of these come with very strong theoretical guarantees, and I'll mention in a minute. If you do vanilla versions of the theory, it doesn't do so well. Local improvement improves the practice. Multi-resolution improves the practice. Lots of things improves the practice. I'm going to not go into those details today. But to talk about the comparison of spectral and flow, because if we're thinking about using these things as experimental tools to probe the graphs, so spectral, it would be nice to have tools that are different. Because a lot of tools really are just the same thing. First cousins or at best siblings or maybe identical twins almost. So it would be good to have methods that are as different as possible. Spectral and flow are that. So spectral computes an eigenvector. You get quadratic worst case bounds. So if you're familiar with Cheeger's guarantee. You can ask, is that quadratic an artifact of the analysis or is that real? In the sense that are there graphs that are that bad? And the answer is that is real. There are graphs that are that bad. Basically the Guattari-Miller type graphs that have long stringy pieces. And intuitively the reason is that eigenvectors are related to diffusions and it takes a lot of effort to push probability mass down stringy things. So you tend to clip those off. And this embeds you in a line. But because you have to stay perpendicular to the trivial eigenvector, it also embeds you in a complete graph, and the duality is actually tighter there. Flow-based methods compute a linear program. You get log n worst case bounds. You can ask, are those bounds tight, or is that an artifact of the analysis? The answer is they are tight. And the class of graphs that achieve that are constant degree expanders. And it embeds you roughly in L1. So you have two methods, complementary strengths and weaknesses. And what we see in a lot of cases is what we compute will be determined at least as much by the approximation algorithm as the objective function, in the sense that there's no point in arguing about conductance or modularity or any objective unless you specify how you compute it. Because oftentimes what we see is determined at least as much by the procedure we use as by the particular objective. So what's going on here is that usually the way you think about geometry is that, I have some geometry, start with a ring and I add stuff. Or you could say I generate it in some way, in some process that I can look at meaningfully geometric. But the reason I mentioned the duality thing because the reason these algorithms come with strong theory. I mean, the modern theory of approximation algorithms basically says for a wide class of problems, you get good approximations and you get good embeddings. So you take the original data set, the graph, and you embed it somewhere. It's a combinatorial place you embed it in a line, in a complete graph, you relax to an SDP, which is embedding you somewhere else. And that embedding means you take the combinatorial object and you sort of filtering it through a geometry. And you get the bounds you get basically because you take the original data set and you filter it through this geometry. You clip things off in various ways. With spectral, you clip off these stringy things. With flow, you clip off other things. And then you get whatever you get. Now, it's not like when you run the algorithm, you're doing this. When you're running the algorithm, you're just computing an eigenvector. But really, under the hood, what you're doing is these procedures. And so, the question is, can we maybe use this as a way to understand the implicit regularization properties? Because if you have 4 million nodes and 40 million edges, you're going to fix a noise if you're not very careful. So can we understand these embedding properties as a way of sort of implicitly regularizing so that we can be confident that the answers that we get are not artifacts of the algorithm, but are really a statement about the graphs? So if you use vanilla versions of any of this stuff, you're going to get terrible results. And the local global issues means if you do use vanilla versions, you're going to get lousy results. So we really had to use local extensions of vanilla global. So I can talk more offline if anyone wants to know more of the details. But cut improvement. Given a cut, find a good one nearby or certify that none exists. So the spectral and flow versions of this. Local algorithms and locally biased objectives. So rather than computing the first global eigenvector, say, geez, eigenvectors are about diffusions. But what if I start at a given node, and rather than diffusing forever, in which case I get the global eigenvector, diffuse for 3 steps, and other things like that. So then I'm getting locally biased versions of these. And you can combine spectral and flow if you're familiar with that. So what's not done, apply these ideas to other objectives. But we're going to be using local versions of that operationally are doing very similar things, and that we have very strong theory for. So it's not just a heuristic. We know, there's a theory-practice gap, but a lot of the cheeky results, a lot of the results you get from flow, you'll inherit in slightly different ways in the local setting. Okay, so to give you a nice picture, so I'm showing you a nice picture here. You should be wary because I told you that, you know, the data is not going to have nice pictures. But to give you sort of an intuition as to what we're doing with the local methods, so I have a graph here, and let's say I start at this seed node and I run 3 steps of a diffusion, or I start at this seed node and I run a few steps of a diffusion. So think of this as a more central node in some sense of the word, and this is a more peripheral node in some sense of the word. And what you see is that if I actually look at how that diffusion behaves, I go from red to orange to light orange to yellow, I quickly touch a bunch of things. Here, I diffuse, and it takes a lot of effort because I can touch these guys pretty quickly, maybe those guys, but it actually takes a lot of effort to go from orange to yellow. And so you can quantify that by looking at conductance, say, as a function of volume, and you see you go from red to orange, and then quickly you go down to light orange. Whereas here you go from red to orange to light orange, and you stay around here for a while, and then you get to that bottleneck and you jump down. So if you look at what's going on here, you can understand as a function of your local environment how these procedures will behave. So this isn't a particularly nice setting where you can visualize it, but more generally this is the sort of thing that's going on. And since flow is doing different things, you'll get something similar, but it'll be different. All right. So here's the awkward empirical fact that you will discover if you do this. So what we want to show here is this plot that I have over here, except not ask phi g. What I want to ask is phi g, let's say, of k, which is the min of s, of cardinality k, of phi of s. So a size result version of the best conductance. So all these plot these x-axis is size, y-axis is conductance, down is good. And what you saw before is that if you have a circle, or you have a triangle, or you have something like this plot behaves this way. All right? The color coding is different algorithms. And what you see is that there's good small clusters and no good large clusters. Now, when I say there's no good large clusters, the scatter plot here is things we found. So that just means we couldn't find good large clusters. But you can use eigenvector-based methods to get lower bounds on the cuts of any size, and you can use semi-definite programming-based methods to get lower bounds on cuts of a given volume. So this is a lower bound, meaning there do not exist good clusters that are down here, that are 50-50, right? And this lower bound is well above that upper bound. So all these plots, everything, this isn't, but everything else I'm going to show you later is going to be log-log, or we're going to be on a log-log scale. And what we're going to see is there's lower bounds here that are above the upper bounds there. So there do not exist good clusters here. So it's possible there's a good cluster there we missed. It's possible there's a good one there we missed. And in fact, we know we missed things with different tools. But we also know that we definitely did not miss anything there because of the lower bound. All right, so this is one data set. Here's live journal. Color coding is different plots. Red's the most relevant one. Black is the same. What's causing this? So think in the back of your mind what's causing this. So red, blue, green is different methods, spectral flow and something else. Black is the same spectral procedure applied to a randomly rewired graph with the same degree distribution. All right, we'll get back to that. But what you see, this is live journal, and you're on a log-log plot. So 100 is the minimum here, and million is there. And you see this on opinions too. And these two are different, but the leading order effect is that you have something small, nothing large. And here's how it behaves in citations and webs, authors, papers, and so on and so forth. So every one of these graphs is different. It's known, web machine files on a single machine tend to link to each other. So this whole plot is pushed down in order of magnitude on the y-axis relative to this. There's certain other factual things like that dip there that you sort of understand. But the leading order bit is that they're all behaving this way. They all have sort of local clustering and not large-scale clustering. All right?
Okay, so the question begs itself, right? I mean, I have two metrics. That's what you take are balanced.
Yep.
They're kind of fighting each other.
Yep.
So are there examples where there's a good need in the Pareto curve?
Yeah.
Because if you were to find, because the question is what's a good cluster?
Yeah, so that's, I think, a fair question to ask. Kevin Lang, who was involved in some of this stuff, asked some questions like that. And I think it
Are there
tends to be
examples? That's
covered.
what they're all wild, like they go like this, you cannot find a good enough trade-off.
Sometimes people ask me, what if you change your definition of community to modularity? How does this behave? And modularity, I told you, is volume. So not surprisingly, if you plot a measure that's basically volume as a function of volume, you're going to go down and down and down and down. So that's definitely the case. So the interesting thing about conductance here is that you're trading these two things off in a very subtle way. So that if you're low dimensional, you go down. If you're an expander, never mind this kink that we'll get back to, but if you're an expander, you have no good cuts of any size. So it's invariant to size scales. And if you're these graphs, you have good small clusters and not good large ones. So you could ask the question about the trade-offs. There's the obvious pluses and minuses with that, right? Now you have another knob, which may be more powerful. And I think, Kevin, I could probably give you a point, something on the lines of Pareto, so something like Pareto-like.
Because one of the concerns we have here, this is my group, is exactly that and say, oh, and even more so, what if I just take expanders? Suppose now I have on the mains weights and on the not weights.
Yeah.
What does it mean? Because
Yeah.
it's come from real estate.
Yeah.
So it's not just I draw a line.
Yeah.
It's very limited. And
Yeah. Okay, so how does our friend Zachary behave? So Zachary's the example everyone tests their community protection algorithms on, and of course it just goes down because the best cut's 50-50. Newman's network science, the same thing goes down. That should be obvious given the way I described things. They both go on the plane or the line, so they're just one-dimensional, two-dimensional things. Road networks, power grids. This is so the particular minima you find are not robust. We're looking at extreme statistics. The particular minimum definitely not robust. The qualitative property of going up or down or being flat is very robust. So anything that lives in the earth goes down. That's just because of this isoperimetric. If you're a chain or a two-dimensional, one-dimensional thing, you've got to go down. And if you're an expander, it's going to be flat. Common network generative models. Preferential attachment is flat. Copying model. Copying model is a model that is like preferential attachment, but by design is designed to reproduce clustering structure. Defined to be triangles. So what you see is that this curve pulls down a little bit relative to that, but just a little bit. And then as a function of size, nothing interesting happens. So you can fit to these very local objectives. And sometimes these very local objectives are good discriminative statistics to categorize different networks. But they really do not capture clustering at any scale larger than 3. And that's because the graphs are random and just for entropic reasons. Now, if you go to 4 sums and 5 sums, you can do that, but then algorithmically and statistically, you're dead. So the question is, how do you get to understand cluster size scale 50 or 100? And the success story here is that we use these spectral and flow approximation algorithms, the worst case algorithms, understanding their implicit statistical and geometric properties. And so we got the sort of statistical capacity control that way, and we were able to scale up because we understood their sort of worst case behavior. And that was the big success story. So lots of hierarchical methods. I don't want to say that a hierarchical method could not reproduce what we've seen, but we went and looked at basically anything we could find, in the order of 10 or something, and they all behave in sort of a trivial way where they go down. And in retrospect, it's obvious because if you have a binary tree, split the 2, split the 2, split the 2, split the 2, it's easy to cut that thing in half. You have one edge, and you have all the nodes over here, so you have a lot of volume and just split one edge. And all of them are variants of that at the end of the day, even if it's not obvious. So this thing is chopped. This is the Robbins bar bias. This is chopped because they have a certain base structure of 5, but basically it's a binary tree with some. Okay. So going down, hit a minimum, go up and up. So what could be causing this? So before I get to consequences of this, so the relationship between small scale structure and large scale structure in these social information graphs is not reproduced even qualitatively. So it's not like you're a little bit off. I mean, not even qualitatively. And this relationship governs diffusion of information, routing, decentralized search, lots of dynamic properties. And as I said also before at the beginning, it also governs the applicability of sort of nearly every common machine learning and data analysis tool. So I think this holds much more generally. Social graphs are interesting because if you're trying to compete to develop better algorithms in a very mature area, you have to compare yourself to stuff that's been built for decades, and the people in that area will try to beat you up because you don't over-optimize particular things. The great thing about social graphs is they're so bad and they're so new that every assumption people have about how the data might be nice is false. And so they're very good test cases for the development of algorithmic methods. And 2, you can really ask very new questions about algorithmic methods for data much more generally. And we even have examples where tools we develop in this context are applicable to other sort of more traditional environments. So the popular approaches are to find some simple statistics of fit, and when you get to diameter, density, routing, some more subtle things, the popular models really typically fail rather egregiously at reproducing any of these more subtle properties. So to give you an example of failings of the small world that can be sort of very localized approaches. So algorithmic decentralized search. So Stanley Milgram, if you're familiar with that, has his empirical results from the 60s. It says, you give your you give a coupon to this guy in Nebraska, can you find his way back to the guy in Boston? You send him links to friends, and the answer is yes. And Duncan Wands and Steve Strugatz had a model in the late 90s, a small world model that said, we can reproduce local clustering and get sort diameter by having a small world model. And John Feinberg said, well, wait, basically any random graph is going to have a small diameter. The interesting thing is that Milgram they actually found them, not just that these paths exist, he actually found them. And how do you get a model that will reproduce that? And what he had to do was start with the underlying geometry and add edges in a very careful way that depended on that underlying geometry. So coupled the local and global in a very particular way. Diameter, density versus time. Everyone says the diameter grows as log n because that's what the preferential attachment. Yeah, let's ask the question. So Salutsos and Leskavec and Kleinberg asked that question, and the answer is that in a range of cases, the graphs densified and the diameters decreased. Surprising result. Very, very, very simple dynamic property. Nothing fancy though. How does the diameter change with time? Exactly the opposite of what you'd expect. And they have a bunch of models, and then the forest fire model that they get, the best one there, does a very particular iterative method to enhance sort of probably the forest fire will spread. The devil's in the details there, but the way what they're doing here is a very local operation that has a fairly ill condition, but has a very global effect. So coupling local and global in a very particular way. And clustering and computing structure. One step beyond opposing triangles. Are there good clusters? And we showed that no, there aren't. At least when you're beyond a certain size scale. So all these have to do with coupling between very local and very global structures. So how do we know this plot is correct? I could spend an hour describing to you how we know that plot is correct. So let me give you the one example that is actually sort of neat because we've followed up on this in a number of different ways. So what I showed you before was a minimum. So actually how we did this, you should think of the network as like an atom that you can't visualize. How do you determine the structure of an atom or a protein? You send in X-rays, you send in crystallography, you measure lots of garbage, and then based on the properties of which you measure, as well as the artifact knowledge of the artifactual physics of the things you sent in, you try and infer what these things look like. So we did exactly the same thing, right? We have these graphs you can't visualize. We tore them apart with spectral, we tore them apart with flow and other things, and then based on, we measured all sorts of garbage, and then we looked at the garbage, and based on knowledge of the implicit geometric and statistical properties underlying spectral and flow, we tried to reconstruct this thing. So what I showed you before was the simplest thing, just take the minimum of this curve. We looked at a lot of other things, but let's not look at the minimum, let's look at the scatter plot. So red is flow, blue is spectral, and let's say we're interested in clusters of size 1,000, right there. So if you believe that conductance is really the right thing, down is good, flow is uniformly better than spectral, all right? And so why even touch spectral? So let's look at different niceness measures, where niceness is something that a downstream person would care about. Is it going to be robust for any of the motivating applications? And so what they'd say is, well, diameter of the cluster might be a proxy for niceness. External to internal ratio of conductance. If there's a very deep cut inside, or if the graph is splintered inside, that isn't so good. So if that's not the case, then maybe that's a niceness measure. And what you see is that by both these measures, blue, you can pick up lots of garbage, so ignore that, but by both these methods, blue is better than red. So what you see here is a trade-off between solution quality and solution niceness. So this is effectively the defining feature of statistical regularization. Except the way regularization is usually implemented is I have an objective f of x. X is a vector in a vector space. And I optimize f of x plus lambda f of g. G is usually some norm constraint or something, some capacity control constraint. And lambda is a toggle parameter that allows you to trade off between solution quality and solution niceness. All right? What we're seeing here is effectively the defining feature of statistical regularization, except we haven't constructed that f of x plus lambda f of g. We're observing it as a function of two different approximation algorithms for the same intractable relationship. So we have other examples of this where the approximate computation in and of itself can implicitly regularize. And that's a big winner in all this for data analysis more generally. Because when you replace f of x by f of x plus lambda f of g, oftentimes you're constructing a harder problem in some sense that now you need to solve that's going to be more robust. And that's going to be a deal breaker if you did a 1 million node graph with 10 million edges. So the question is, can you fold this regularization into the approximate computation so you can scale up, but also understand what the robustness properties of defining are? So the answer to that is yes. So what's the interpretation of these graphs? So I'm almost out of time, so let me just tell you sort of the bottom line of what the graphs look like. So I can talk for 1 minute more or 1 hour more, or anything in between. So let's give me a number. Okay. All right. So so what could be causing this? So what's maybe, if you've read any of this stuff, you maybe know the answer, so don't answer. But what's the simplest model that might explain this property, right? So the profile plot goes down. The simplest thing might be, a discretization of the plane. Something that's a little bit. If it's flat, constant degree expander, random graph, reasonably dense, whatever. What's the simplest possible model that might explain the empirical fact that we have a minimum? So there are good conductance clusters at small size scales, but not at large size scales. Right? So I'll give you the answer in a slide or two. But
Scale. Behavior with respect to scale.
So there's a couple of issues, but the simplest question is I have good small conductance cuts, but no good large ones. So what's a graph model that would reproduce that?
Oh.
So I'm going to give you the answer in a couple slides. So back to the empirical. So let's define a whisker to be a maximal subgraph detached from the network by removing a single edge. One edge, some number of nodes. So empirical fact. Global minimum of the profile plot's a whisker. Now on one hand that's obvious, because if you have a bunch of stuff connected by one edge, it's a lot of volume, a little bit of surface area cut it. But on the other hand, if the graph really were a discretization of a low-dimensional place, you wouldn't have a bunch of stuff connected by one edge. So what you want to say is these whiskers are just nuisances. They're not real, cut them off and get to business. So if you cut them off, you're cutting off 40% of the nodes and 20% of the edges. So that's a deal breaker, right? When you go and you search on Britney Spears, everyone knows you want your web page to look at your pictures or Wikipedia page, whatever. If you search on a term that no one's ever seen before, there's not much you can do. The interesting stuff is in between. How you define in between, and it goes by the name. You push mass out of the proverbial heavy tail with a long tail. Is the way it's sometimes described as a popular literature. So you can't be throwing that out. I'll show you what happens if you do throw that out, but you can't be throwing that out. Now let's define the core to be the rest of the graph. So an empirical fact is the global minimum of these things is a whisker. But you could ask, what if you're willing to eat this? What is the network profile plot of the core look like? And it turns out the core itself has a core periphery structure. So red is what I showed you before. Green is the profile plot of the core. So I've eaten that 20%, 40%, threw that out. And I say, the core itself has a core periphery structure. The core itself has a bunch of small clusters, no large clusters. If you look at what's achieving the minimum there, now it's column 2 whiskers, a bunch of nodes connected by 2 edges. And you can iterate this process in a couple different ways. You see the same thing. You start filling the core off like an onion. So these small little whiskers, these nuisance things, apart from being nuisance things, that's all there is in the data. Everyone is a whisker. 1 whisker, 2 whisker, and so on. Right? And understanding their properties is essential to understanding the graph, because you can't be throwing them off away to understand the graph. That's effectively the property of the graph. If you do that a half dozen times, you're left with a small cluster, very high degree notice, for instance. So everyone else is in one of these whiskers.
So if I look at algebraic stuff, right, we can look at 2 cycles, 3 cycles, 4 cycles, or I do like stuff that's made out where I try to do at the clusters over scale. And they will do this. I know it's difficult to compute, but people have done it in some examples.
So I don't, yeah, so, okay, so.
So I'm looking into some of the recent work in your department.
Yeah.
Computation and all that stuff.
So that's something like that should work. So I know Gunnar Carlson, I know Steve, I've talked to them about this. The philosophical approach is saying I want to get qualitative properties of the data.
But they also claim, right, because I've talked to this a lot, that this throws away minutia, this approach. In other words, if you have a real core,
Yeah.
and I go up and down in scale, and the other key word is the metrics, because y contact us and all of that.
Yeah.
And I should be able to capture.
So something like that should work. The way they're formulating the questions now doesn't seem to. And I think it's because they were still working in the Hilbert space.
Well, it's not only
And-
that, maybe the metrics that scale users are in mind, and maybe disagree, but some of the metrics used are actually naive as far as the meaning of it.
No, that's true too. Yeah.
I use correlations and space in a product Y.
Well, the point of the Hilbert space is really it's just a low-dimensional space in a sense. You can raise that to high dimensions, but expanders are the graphs that will embed least well in any Hilbert space of whatever dimension.
Yeah, but there's a good question. But there's a good question. When you embed the graph, what should be the space where you embed it? And then we know,
Right.
vector, Rn-like spaces are not the correct one.
So they're not the correct one, right? So that's what, so the Hill, that's, I think at the end of the day, basically it's because if you're in an Rn, you have these isoperimetric properties that are local, global, you're the intuitive thing. So you need to get outside of Rn to capture some of these properties. So the combinatorial graphs do that. You might be able to do something in bottleneck space with local geometry of bottleneck spaces or something. The danger there is that the people who do bottleneck spaces probably aren't going to worry about these niceties and vice versa. But you could be able to do that.
I mean, it's non-linear spaces, like hyperbolic space and stuff like that.
Okay, so I'll mention a little bit, maybe we can talk offline.
We'll have the informal.
Okay, but yeah, so the hyperbolic spaces, we have a lot of ideas on, we've been looking at that, and intuitively the degree of heterogeneity coupled with a reasonable amount of randomness in some sense means that a hyperbolic metric should be a little bit more appropriate. The way people are doing it now doesn't quite do it right, and we're actually spending a lot of time thinking about that, so I can, but I think that's actually, some version of that would be a good avenue. So, the simplest possible model that will reproduce this. So everyone beats up on error-Schranien. So the second simplest possible model that will reproduce these properties is the following. Let W be a parallel degree distribution vector. Connect nodes I and j with probability Pi j that depends on the vector. Parallel random graph, the charm sort of stuff, if you're familiar with that. Theorem. You have a dip in the profile plot of size log n, and it's log n deep. And if you go a factor of 10 larger, there's no dips that are more than a constant value. And what you wanted to say is, power laws. Power laws are responsible for all these problems. And so let's land on the power laws. You see exactly the same thing with error-Schranien. All right? Now, error-Schranien has a parameter. I think I have it in this deck. But so far I had it. Let me just put it on the board. Error-Schranien has a parameter that says, what's the connection probability? If your connection probability is less than 1 over n, you're a bunch of tiny pieces. Don't worry about that. If your connection probability is greater than log n over n, or log squared n over n, you're a fully connected graph. So in some sense, things are measures concentrated and you're in the asymptotic regime. If you're here, you're not fully connected. So say p is 2 over n, you're not fully connected, right? That's a very difficult regime to work in. And the fraction of graph theory papers that work in that regime is probably 1 in 10,000 or 1 in 1,000 or something, because it's a very hard regime to work in. If you set p to be 2 over n, not fully connected, but now work with a giant component, throw away the small stuff, which is reasonable. In all these applications, you get a big graph, you always have some small peanuts you throw away. So work with a giant component and ask, what's the profile plot of that giant component? And you'll see exactly this. Now, the set of nodes that achieve it, intuitively it's because you're very sparse, you have 2 or 3 edges on average. And these are little tree-like things connected by 1 or 2 edges. Now you want to say tree-like things, those are just nuisance factors, then you're right. But we showed you what happens with the nuisance factors. Now, this plot does not go up relatively gradually. The real data does. So this does not explain the relatively gradual increase. And that's very important for understanding how the local structure couples to the global. Because here, you're on a golf course, right? The state space is flat, boom, log n dip. Boom, log n plus 1 dip. Maybe there's a log n plus 2 dip on the other side of the world. You'll never find it, right? So what if this log n dip now is in fact 10 log n because you have a lot of local clustering or something. So you should think of these real graphs as being quasi-isometric to an obscenely sparse random graph. Quasi-isometric in the sense that a discretization of the plane looks sort of like the plane if you squint at it. Right now, it's not fair to formalize that in terms of quasi-isometry to a random graph, and that would be an important open question raised by this. But intuitively, you could think of that, right? You're something like a sparse random graph, maybe with a degree of variability. And you close triangles. And for that matter, you close quadrangles and 5-gons and 6-gons, and you have some sort of local structure. That at size scale 50 or 100 looks like exactly. Looks like your 100 friends on Facebook. Looks like something like this. If you go to a size scale 200, 500, 1,000, 10,000, the degree to which it looks nice just gets worse and worse. So that's what these clusters look like. So what does the data look like? You just squint at it. Is it a hot dog? The advertised printed phrase graphs I showed you, we had 3 nice clusters, is a hot dog. left half, right half, it was a long hot dog, it was a middle, right? Left half, right half. And you get a good cut in the middle, 50-50. Is it, I said a point, but that's a little odd. You know, is it an expander? Is it a click? Is it just very, very well connected everywhere? Or is it some sort of tree, in quotes? Or some sort of tree-like hyperbolic structure? So let's say you want to take a squint at the adjacency matrix. You know, alpha, beta, beta, gamma. So if the graph is morally low dimensional, whatever morally means, you know, alpha and gamma are large, beta is small. The profile plot will go down, spectral partitioning and anything in the world will work pretty well. You cut it in half, it occurs. The graph could be bipartite, in which case these two guys are large, not small. The graph could be an expander, in which case that is all small and sparse. Or a clique, in which case that's all small and dense, but you know, all pretty homogeneous. Or you could have some sort of core periphery structure, which basically says that this is large, that's medium, and that's small. And if you fit the data to this, you take the large and small graphs, you look at a hot dog, or a tree, or an expander, there's the numbers, and if you color code it, you get exactly what we had before. So you have something that, you know, behaves one way, you have a core periphery. Now this is a nested core periphery, so it's trickier, but that's basically what you're going on. So the simplest explanation for these leading order bit in all these social information graphs is extremely sparse Erdős-Rényi. But you know, take a step back and say, what does this mean? What this means, you know, there's no claim that Erdős-Rényi is the right model for how you link on, you know, click on links or whatever. The claim is that the generative mechanisms are such that the data is extremely, extremely sparse. If you generate a factor of 10 more data, you go into sort of, you know, it's not like you generate a factor of 10 of the same data. You get better time resolution, better spatial resolution, better demographics and geographics. So you never hit the asymptotic regime. You're always very sparse. And obscene sparsity plus a reasonable amount of randomness means you don't hit the asymptotic regime. Measure fails to concentrate. And so power law graphs are just one way to do that. You know, the extreme degree of variability means that you don't get to that concentration. And the iterative forest fire model I mentioned earlier gives you a way to put a little bit more local structure on top of that. So you should really think of the data as a little local pocket of structure on top of global noise. It's not SVD or PCA, so global low-dimensional space with a bit of noise. It's a pocket of thing here that may be a local version of spectral, we'll find, a pocket of something over here. And this pocket gets worse and worse as you get larger and larger. It embeds less well in 2, 3, 4, 5, 10 dimensions to such an extent that at some point it's almost meaningless to talk about that. You know.
So is the cave model small noise and global structure or local structure and global noise?
This caveman thing?
The caveman.
So the caveman, the way it's,
Your terminology, where you
so the way the caveman, that's the way the caveman works is that's like this hierarchical thing. So the caveman
where
is,
would you put it?
I mean, that's, the caveman is this.
Yeah.
You have 10 clusters, they're pretty well connected. How do they connect? You either put the cavemen on a line because they live on a river, in which case they connect to the nearest neighbors, or they live on the plain, in which case they connect to the second nearest neighbors. It's not impossible that you could connect them with a random graph type structure and reproduce something like this, but existing models don't.
The example, you know, where you use multiple caves, right? So I have cavemen and they talk but then one of them goes far away and another one.
So that's a small world model.
Right.
The caves are the threesomes, and that's a small world model. The small world model doesn't reproduce. I didn't go into detail, but the small world model gives you a little look. It's basically flat. So it's not the case that it's impossible to reproduce with the caveman model. It's just that the caveman model people had a couple of years ago when we did this. But you might be able to play with the parameters and do that. And that relates to the hyperbolic embedding that caves out of the concrete disk or something. So let me wrap up. We had this slide before. So we've been talking about the property of social information graphs. And you know, basically there's little local pockets of structure on top of global noise. I mean, I'm willing to predict, we're actually looking at, you do MNIST digits, you do any bunch of other things that have been very, you know, studied very extensively, you'd see similar properties in those things. And you know, in fact, you have. So basically the question is, you know, more generally for large scale data analysis, you have these sorts of things appearing under the hood in a lot of cases. There's a lot of things that people would find unpalatable, like a recursion depth of order n. And so people either cook the data or they'll only look at data that's relatively nice and so on. So I think there's implications much more generally for a lot of large-scale data problems. But at least at the more immediate level, that's looking forward to the more immediate level looking back, you know, people say explicitly in a few cases, but have in the back of their mind implicitly, that as graphs corresponding to these complex networks become bigger and bigger, the complexity of your internal organization increases. So that, I think it's fair to say, is simply not the case. The empirical evidence, some of which I review today, is very strong. And really, I think this should be obvious. Now, it's not obvious how to couple that with the desire to find new clusters, to do something statistically or algorithmically meaningful. And so that's why it has this much more general implication. So that, let me wrap up.
So, the question is,
Well, thanks for a terrific tour of a variety of methods, and it's just very different from the way we look at graph problems and kind of problems we solve. But I'm struggling to reconcile your initial motivating question, which was, you have sports, you have gambling, and you were looking for a cluster that was sports gambling.
Yeah.
And I never got to see how the cluster methods identified whether there was a sports gambling or not.
Okay, so I don't know. This is a citation graph, so I'll call it sports gambling, even though it's not. But that, well, that's size 100. That is a sports gambling cluster. So that.
I don't get it.
That. So if you look at, if you want to test out, if you look at the advertiser graph, so these are, but look at the advertiser. So we're looking at extremal statistic. There's a lot of other stuff buried up here, right, that you could pull out. If you look at these, at what we actually pull out,
Right.
and you say that you have meta information, like the advertising tags, like the keywords,
Right.
and you look at a 10,000 node cluster, and you say, is that a meaningful cluster?
Right.
There's definitely a lot. The answer is, yes, you're pulling out something much more meaningful than random. And you can say this is a cluster that is meaningful in some sense.
So you
That
find
is
a cluster, I believe the methods will find a cluster,
Yeah.
but then how do I know, there might be 6 or 8 clusters around, which one is a sports gambling, or is there at all? Is there a sports game? Maybe there is no sports gambling cluster. So what's your metric for demonstrating that there is or there isn't a sports gambling cluster?
Okay, so there's a couple of questions there. So I didn't show this, but we have a bunch of data sets where we have some notion of ground truth. And if you look at the ground truth clusters and ask how does the profile plot behave for those ground truth clusters, it also goes down and then goes up. All those notions of ground truth are very faulty. And if you look at the ways in which they're faulty and the details of these plots, you can sort of rationalize it. When there's a stronger homogeneity in terms of generating edges or links or something, some markets where there might be more agreement on what the terms are or whatever, you can get a little bit more homogeneity. And so so they all go up, but sometimes they go up to the random basal level, sometimes they go up to something below the random basal level. So we can use ground truth like that. If you use ground truth like that in a bunch of applications, and in particular in the advertising one, you can pull out clusters of size 10,000 or whatever that are definitely meaningful. Now, I don't know how to cross-validate or whatever, that's part of the issue. So, but you can definitely pull something out that's meaningful. So there's 2 things. Three things. One, we don't know how to do that cross-validation because it doesn't map.
I believe you can say
traditional
it's meaningful from a graph theoretic connectivity.
No, it's meaningful from a graph theoretic.
But then how do you?
But it's meaningful from the, if you look at that node,
Right.
not everyone is about sports gambling. You get something about your mother's flower market.
Right.
But, there's definitely, 90%, pick some number, are about something related to sports gambling.
That's sort of like a little more rigorous way of.
So that's not a graph theoretic measure, that's meta information that you're using to validate. Now, how do you really validate that double blind? No one knows, but that's some meta information. So one, you can pull that out. We don't know how to evaluate that, no one does, and anyone that tells you they do is, probably doesn't, because it's, that we have a graph, we don't have a bunch of vectors, and so most of the validation methods deal with vector space, statistical methods, and so it's hard to map that onto graph stuff that's this sparse, right?
Yeah.
So that's definitely a problem. The other thing is, it's actually hard to find this cluster because it's not such a stable problem. If you're finding this cluster here and you have capacity control because the sports gambling market doesn't interact with over there because you're on some one-dimensional thing, then you can, a lot of statistical methods will be reasonably robust, you can refine it or whatever. But if the sports gambling market is sitting next to a sports market, which is probably a much bigger, much more heterogeneous, noisy, unstructured thing, and you use any of these diffusion-based tools or anything, you're quickly going to get your mass sucked out there, and you're going to be dead. So the tools don't deal especially well with that, these local global properties. And there aren't good statistical methods to validate that. Those are big open problems.
Okay. I think that's interesting further. Just one other comment is, I am, in our work with different networks, we get really interested in the range of networks. We do see, large networks with thousands of disconnected components.
Yeah.
They're all small and they're all disconnected. There is no one giant component that you can go to work on.
Yeah.
And that's interesting.
Okay.
And there are other times where you have a pretty strongly connected one, big blob, or
Okay.
what we've come to see is sort of interesting patterns, like if you do, GOP on, or Democrats on Twitter, you get two pretty strong clusters. We see that pattern now of the cluster, the graph of conflict. If you get conflict topics, you find a well-connected component that supports one side, a well-connected component that the other, and there's a few hairs going back and forth, but that's a pretty strong thing. So we're after identifying what are the kind of structures you see, not necessarily finding a good partition.
Well, but I mean, it's the thing of the Congress data you were talking about. So the Congress data
Yeah,
is
that was
bottleneck
also
here,
a straight partition.
and you have time shots for the last 100 Congresses. Where it gets small in the old days. So the last 40 Congresses where you have more than 100 senators roughly. If you say, I want to pull that, I can use as my seed node, I was doing a local spectrum, I can use as my seed node, a couple senators from whatever Congress was in 1970, 1960, and I want to diffuse around a bit. The voting patterns in 1960 were very different than in 2000 in terms of polarization. There was a bunch of them. If you diffuse around here a little bit, you can see that very easily. The things are just much less stable because you have almost three parties, and the two are overlap a lot more than in 2000. And in addition, if you want to resolve the temporal axis, the fact that this thing's almost aligned is very structured. So it's a lot easier to deal with something like that than the general social graph. So if you take a step or two beyond that, you touch everything. But in that case, we apply these methods there. In that case, we want to pull out something based, 1960 plus or minus a couple of years to understand the heterogeneity there. So I mean, the clustering is the question as a function of size. But if you look at the voting pattern for that Congress data set, as a function of size, the best partition is early times, late times. And then inside it, you get some more structure. So in that case,
Well, they
it's
do
gonna be
evolve
very different
based
here.
on the political issues, and that's what our political science friends want to know about. So, you have, high degree of connectivity among Midwestern Democrats from caucus together, and, the cohesion in that 2007 graph was good for Democrats, but weak for Republicans, but that's changed.
Yeah.
So
So
you
we
do
thought a little
change.
bit about that, and I haven't, not as much as I'd like. I mean, the way I think about it is that what's going on inside the size scale 100, and what you're talking about is what's going on inside that size scale 100. Because I suspect that Congress is a nice data set to test because the large scale architecture is fairly straightforward. It's a line, and you can ask what's going on locally, like you're saying. And presumably, once you figure out how to deal with algorithms that deal really well with that question, then you can say, okay, now I just need to sort of regularize or tune it so that I can ask the same questions in a graph that's much less structured, like the social graphs. Because I'm willing to bet that a lot of these, I said every graph's an exception to the rule, right? That some of these would have analogous patterns in terms of what's going on. But finding them in these graphs is just much harder than in Congress because at larger size scales things fall apart. So the way I think about Congress is that it's a good test case for
To
those.
answer your question, okay, or the dialogue that I'm hearing is the question that nobody can answer if one tells some mathematical results that I know of is there a taxonomy? Because you say
Right.
you want to see different graphs.
That's right.
But define for me different types of graphs, because if every graph that has a link that is different is a different class, it doesn't mean
No,
anything.
no, no. I think
And
we
then,
want to.
and related to the taxonomy is this taxonomy robust to any, adding a little node or anything
But
like
it's
that?
pretty dramatic when you consistently see the pattern of conflict. That's a pretty interesting, one. There's also the pattern of a brand, a company that actively creates a social network has a different structure that's, it has a strong separate component, and then there's a lot of disconnected,
Disconnect does not bother me, Ben. The way we would look at this is at least we would look at two metrics, okay? How well the clusters are separated from each other,
Yeah.
and how similar the nodes that you put in the same
Yeah.
graph are according to the attributes that you put there.
Right.
And then you start looking at reducing the attributes and say, is this similarity destroyed or not? And I
That's
think
why
that's-
I was pleased with your question that said, hey, isn't there something about the nodes that you want to look at, not just the edge connectors? And yeah, I think there is.
So I think you can use this. There's a lot of people in machine learning that think.
I think we should let people
Yeah.
go here.
Okay,
Carry on. But thank you.
Okay.